Namaste. Welcome to this channel, Dr.ARM's Chemistry Frames. We were discussing the chemistry of 3D elements, and in that case, now we are studying the point that is stereochemistry. Under this point, we have seen some previous information regarding the various types of isomers, that is structural isomers, and now we are going to see this stereoisomerism. So today we will see this stereoisomerism. Here the stereoisomerism, or you can say distereoisomerism. So this study help us to understand what are the cis and trans forms or trans-isomers of these various types of complexes. The square planar complexes are between mer and peg isomers of an octahedral gas. So we know that the tetrahedral geometry does not exhibit the cis and trans forms or trans isomers, but square planar complexes are there to explain the cis and trans isomers of certain complexes. When we consider the octahedral isomers, octahedral complexes, they also exhibit the cis and trans isomers, and in addition to this, they are also exhibiting the facial and meridional isomers, meridonial isomers. Now we will see some of these examples. So in case of octahedral complexes, we have seen just in that tetrahedral complexes does not exhibit cis and trans isomers, but square planar complexes only exhibit these complexes. But the presence of chiral characters are also not easily observed in square planar complexes. So that will be discussed later on in detail. Now we will see the octahedral complexes. In this case, if we see the physical form, that is Cl, CO, NH3, then NH3, then this NH3, then this Cl, then this Cl. So this is facial form. Here you will see, we will see another example of this facial structure. And so this is also fish. Now we will see another meridonial structures in which you will find NH3 CO NH3 and NH3 Cl this is also Cl and these are meridonial isomers. You will find that in case of this facial isomers, you can consider the face which is defined by, so this is a phase defined by these three NH3 molecules. Similarly, another phase is also defined by these three Cl. So here the characteristic of this facial arrangement of three ligands. So three ligands occupy the positions of triangular face. Triangular face. So this is triangular face, and therefore this isomer is called facial. Similarly, you will also find here this face as well as this face is also showing the triangular faces. So therefore it is called a facial isomers. Then here it is another, that is meridonial. So in this case you will find that the three ligands. So if you consider the plane, like this, so this plane consists of these three ligands, this 1, 2 and 3 ligands, which are bisecting the molecule. So this molecule is divided into two parts or hulls with the help of this NH3, 1, 2, 3 NH3 ligands, and this Cl is out of the plane. Similarly, the three ligands, we can consider this 1, 2, 3. These are also present in the plane which are bisecting the molecule. Similarly here, you will find that this nitrogen 1, can consider 1, 2, 3. These are having also similar plane in which you can consider the plane like this. Like this. So each occupies the 3, 1, 2, 3 nitrogens in the same plane which are bisecting. This is 1, 2, and this is 3. So the 3 nitrogens are means coordinating points or atoms are lying in the same plane or in one plane which is bisecting the molecule, and therefore such isomers are called meridonial isomers. Further, structure of such species or molecules is determined by single crystal X-ray diffraction method. Now we will see another the methods by which the structure of such isomers are investigated or confirmed. So first methods for structural investigations. So first of all, we have seen that the method is X-ray, single crystal X-ray diffraction. So this is a separate part, and that will be discussed, or that is also always discussed in some other places where we are considering the physical methods or in physical chemistry. Now in second method, the method is vibrational spectroscopy. In case of such method, we know that when the bond is containing the two different atoms of different electronegativities, or which are asymmetric, having asymmetric charge distribution, then they can show under the influence of, or when the molecule is irradiated with IR radiations, the molecule shows absorptions, and the energy absorbed in such molecule is used to, or it is converted into vibrational transitions. Means the molecule gets excited and undergoes vibrational transitions, which are stretching or bending type, and which are exhibiting at different frequencies. So this type of vibrational spectroscopy can be explained with the help of simple examples. For example, in case of this PtCl2, PtNH3+Cl2. So if we take this example, so it has this unit Pt, So this has unit PtCl2, and this PtCl2, depending upon the symmetry or asymmetry, it becomes IR active or IR inactive. When the molecule is asymmetric, both cis and trans positions of the isomer exhibits the absorption transitions, means they are called IR active. So these molecules having cis and trans forms, they are IR active. These are IR active. But when it is, the transition is asymmetrical. When the vibrational transitions are asymmetric, then these both types of isomers, cis and trans, are IR active. But when the transition is symmetric, when the molecule is symmetric, molecule shows symmetric transitions, symmetric stretch. In case of this PtCl, then this shows that only the cis isomer here, the symmetric stage for this PtCl2 unit is IR active only for symmetric stretch, we can see. Stretching or symmetric stretch or stretching is IR active for cis isomers only. Cis isomers only. Because during this symmetric stage, the distribution of charge is different. But when the position is trans, or when you consider the trans isomer, after symmetric stage, the electron distribution or charge distribution on the bond is symmetrical, and that is why that is not IR active. For example, if we consider example, that is when platinum Cl is there, then NH3. So this is square planar complex. And another example is Cl, platinum, Cl, NH3 and NH3. So here you will find that this is a trans isomer and this is cis isomer. So here the asymmetric stretch in this case asymmetric stretch in this case will show IR absorption, IR active is absorption at 365 per centimeter. 365 per centimeter. In this case, so the asymmetric stretch can be shown in this way. IR stretch can be shown in this way. This is asymmetry. If the two arrows are in opposite direction, that will be symmetric stretch. Means the Cl is moving in this direction, this Cl is moving in this direction, that is called symmetry stretch. But these both Cl are moving in one direction. So that gives asymmetric stretch. And in that case, we have seen that the absorption of ion radiation takes place at 365 per centimeter. Here in this case, if the stretching is taking place in this, that is, this CL is moving here, this CL is moving, but it gives ion absorption at 330 per centimeter. Means one CL is moving closer to this platinum, another CL is moving away from this. So this is also asymmetric stretch. So this is in case of this platinum unit, that is PtCl2. Now we will see another example where we can find the vibrational spectroscopy or other types of spectroscopic methods. Now we will see another method where we can help, or we can take the help of instruments, and that is the NMR spectroscopy. NMR spectroscopy. So this NMR spectroscopy gives us the peaks or the bands in the NMR spectrum, which are representing the excitation of nuclei, and this is possible only when if the atom involved in this molecule has the nuclear spin quantum number I½ means the atom of the ligand should be or should have odd atomic odd mass number or mass number. For example, 31 phosphorus. So it has mass number 31. Means there is one odd number, and this is having the spin, nuclear spin quantum number, that is I, and this is 1/2. So nuclear spin quantum number is designated by I symbol, and it is this 1/2. For example, if we take the complexes containing ligands of phosphorus, that is phosphate, so we can have this 31P in ligands like phosphate. The ligand is like a phosphate. So this spectroscopic method or diagnostic method for studying the isomers, which are cis and trans in nature. For example, cis and trans isomers of square planar complexes. So if we see the cis and trans isomers of square planar complexes, cis trans isomers in square planar complexes. So here we will see NMR spectroscopic probe. NMR spectroscopic probe. if we take the example of platinum, which is square planar in nature, and it contains phosphorus as a donor atom in phosphate. So if we take the example of, so the information of NMR spectroscopy is available for us to find out which is cis and which is trans arrangement on these ligands. So in this case, when the ligands, when we consider platinum as a metal, this platinum has naturally occurring 6 isomers. It has 6 natural isotopes, and out of this only one isotope, that is 195 is here NMR active, and it is 33.8% abundant. This isotope is 33.8% abundant. And here we will see some examples. So the nuclear spin quantum number, as we have seen earlier, the I value for this phosphorus is 1/2. Now if we take the example of, if we take this example of a complex platinum PtCl2 PPH3 twice, then in this case you will find 2 atoms, 2 centers of the atoms are NMR active. So one is this platinum, another is this phosphorus. So when 2 centers are exposed to the radiations which are responsible for this spectroscopy, NMR spectroscopy, so they will show absorption due to this platinum as well as this phosphorus. And when in such case they will show spin-spin coupling. So because of these 2 active centers, they will show us spin coupling, spin coupling between these 2 platinum, that is platinum 195 and this 31 phosphorus. So this will give us, so these 2 nuclei will give rise to satellite pits. So they will give rise to satellite pits. So in this case, you will find that the radiations absorbed will show or will be considered in terms of hertz. The coupling constant in this case, coupling constant for both these cases, for platinum and 35, is given by J phosphorus for P, this platinum for PT. JPPT indicates the coupling constant, spin coupling constant, which includes the spin due to this platinum 195 and this 31 phosphorus. So in this case, we can take another example. So here you will find that in this complex, the coupling constant J has value about is 2000 to 2500 hertz. 2000 to 2500 hertz. This is for trans this value is for trans-isomer. So this is for trans-isomer. And now for cis-isomer, this J PPT value is for cis-isomer, this J PPT value is 3000 to 3500 hertz. So this will clearly distinguish. For trans-isomer the value is 2000 to 2500, but for this is the value is 3000 to 3500. Then we will see another example of this complex PtCl2 PnBu3 tertiary butyl twice. So here there are both centers, means phosphorus as well as this platinum, both are having spinning the odd nuclei, and therefore they are showing both cis and trans-isomers. So if we take the cis variety, cis form, it will show the absorption at about, cis isomer will show JPPT at about 3000 to 3500. This is for cis and trans-isomer. For cis isomer it is 3508, 3000, 3508 hertz, and for trans-isomer the value is for this J PPT is about hertz is equal to, you can say, it is not ranging, at 2380 hertz, 2380 hertz. So these values will clearly distinguish between the cis and trans-isomers, and this will also prove that there is JJ coupling. Now if we see the structure of this NMR spectrum, you will find that so the values on this scale are like this: 10.0, here it is 0, and the value here it is minus 10.2, that is delta per ppm. So this is using 162 megahertz 31 phosphorus NMR, 31 phosphorus NMR spectrum of this complex. So here you will find that the distance between these two is it is J ppt. This is 3508 hertz. 3508 hertz. So in this way, the NMR spectroscopy can be used. Similarly, we will see again another diagnostic information which is provided by this NMR probe. Also, so this is in case of square planar complexes. Now, if we take another example, that is having rudium RH, rudium RHCl, PR2, PR3 twice, L. So here, this L is neutral. The L is neutral. This RH is in first oxidation state, and this RH and this phosphorus are the nuclei which are suitable for NMR probe. Here the rudium is monotopic. This is monotopic, means that is 100% one of isotope with 103 RH rudium having I 1/2. So in this case, the cis isomer here, the cis isomer will have J spin coupling between RH and this P, that is PRH. PRH is approximately equal to 160 to 190 hertz. And for trans isomer, this JPRH coupling constant is 70 to 90 hertz. 70 to 90 hertz. So this will also help us to confirm whether the isomers are possible or not. So this complex exhibits 31p NMR spectrum of RHCl PR3L, exhibits a doublet which is having JPRH, a coupling constant characteristic of a particular isomer. These values are characteristics of a particular isomer, and therefore we in this spectrum of this, so we can consider the 31p NMR exhibits a doublet, which is giving these two values which are characteristic of, which are giving these two values which are characteristic of these coupling constants. So the existence of isomers or molecules in different structures, for example TBP, trigonal bipyramidal and square pyramidal, square based pyramidal. In case of, so we will review this. So in another example, you can see in NiCl5 3 minus. So this is also a special case. The existence of ions or molecules in different structures can also be found. That is, one can say TBP and another is square based pyramidal. So these both structures are also confirmed or by using the nmr-spectroscopy. Now, in case of another, similarly we can have another example where we can have this nickel. Br2, then PZ, PH2 twice. Here BZ means BZ is benzene. Again, so the two forms are distinguished by fact that they exhibit different magnetic properties. So here the two forms, that is cis and trans forms, can be identified on the basis of different magnetic properties. So they exhibit different magnetic properties. So in this way we can distinguish the cis and trans isomers on the basis of magnetic characters. So with this we will stop our discussion. So please subscribe to this channel and please press like button and bell icon so that the video prepared will be sent to you immediately. So thank you very much for watching this video.